Okay, so we finished chapter 1, which was a very broad introduction to history of oceanography, explorations, etc. In the book, you have chapters 2, 3, and 4, which are looking at very interesting things on continental movements, how they relate to some past climate, ocean sediments, marine sediments, biological provinces, and so on, which we will not look at right now. Some of it we'll come back and look at later on in other contexts in later chapters of the same book. Right now, we will look at water and seawater, and we'll start by looking at the overview of the chapter, where we will basically have some introduction to how water has many unique thermal properties and dissolving properties. We all know that on Earth it occurs in all three phases: in solid phase as ice, in liquid phase as water, and in gaseous phase as water vapor. And seawater is different than water because it has, of course, salt. We will see how much salt there is and what difference it makes to the properties of water, and how the sea salinity in the water comes about. And we will look at the properties of seawater in space, longitude and latitude, and how these properties are actually determined. What are the processes that actually determine the properties, right? So the presence of water, as far as we know, makes life possible. In chapter 1, I briefly said that now we have evidence of water on other planets and moons of planets in the solar system. So this is one of the biggest things that everybody is always excited about when we do space exploration: is there life elsewhere in the solar system? That would be exciting because, as I said before, we don't even know if life actually originated on Earth itself, or it got originated somewhere else and got thrown onto Earth, right? So organisms, as we know, including our own body, is mostly water. Our body is almost 65% water, and our blood is almost 83% water. So water is obviously very critical. The structure of the atom, when Niels Bohr proposed it and won a Nobel Prize for it, was simply viewed as a kind of a nucleus which has either just protons or protons and neutrons, and then you have a cloud of electrons around this nucleus, right? So the number of protons is critical. That's what defines a particular element. And some elements, like hydrogen, may not have a proton, whereas most other elements, starting from helium, have protons and neutrons. That gives us the mass of the atom. Plus you have cloud of electrons. Protons, as we know, have a positive structure, and electrons have a positive charge, and electrons have a negative charge. And when you have equal number of protons and electrons, you have a neutral atom, and the bonds that hold these together are very strong, which is what is used to release energy when you do nuclear fusion or nuclear fission, right? So subatomic particles in the earlier on were just considered to be protons, neutrons, and electrons, but since then we now know that there are particles like subatomic particles like quarks and muons and nuons and so on and so forth, which we will not talk about. So it's a number of protons that distinguishes chemical elements. Molecule is two or more atoms held together by shared electrons in covalent bonds, and that's the smallest form of a substance. So H2, O2, for example, are molecules, and they are substances that are freely existing. So that's the smallest form of a substance, other than many compounds we create by combining multiple molecules. So let's stop this introduction here and come back to look at the structure of water molecules and how it comes about.